Let's talk a little bit about partial derivatives and interpreting them. Actually, let's start with a regular derivative. So if I imagine I have a function f of x, which is a function of only one variable, x, and I want to know how much does the function change for a little bit of motion in the x direction. Well, I'll denote the small change to the function as df, and that small change of the function df is the slope in the x direction times the little bit of distance in the x direction, dx. Or I could write that as df dx, since df dx is the slope in the x direction, and then times dx, the little bit of distance in the x direction. So that's how we would think about how a function would change in one dimensions. But what about multiple dimensions? In particular, let me think of two dimensions so that I consider the height of some surface. So my function here, z, is the height of a particular surface. Think of it as a hill, for instance, and it's a function of x and y coordinates. And I want to know how much does the height change for a little bit of motion in, say, the x direction, as shown here. So I have a little bit of motion dx in the x direction, and the height will change in the z direction as the slope of that hill in the x direction times the little bit of distance in the x direction, dx. Well, the way we're going to talk about the slope in the x direction here is we're going to write that as partial z partial x instead of derivative of z with respect to x, where that partial derivative means here that we're only considering distances and motions in the x direction, and y is effectively a constant for this calculation. Of course, I can do something similar for the y direction. I could ask how much does the height change for a little bit of motion in the y direction? And the result is something similar, that the little bit of height change for motion in the y direction is the slope in the y direction times a little bit of distance in the y direction, or partial z partial y times dy, where partial z partial y is the same thing that we had for partial z partial x, but now we're moving in the y direction instead of the x direction. Okay, but what if I wanted to move in both directions at the same time? Well, I can move in both directions at the same time if I include the little bit of height I gain in both directions separately. And so the little bit of height change that I get in z, dz in this case, is the slope in the x direction times dx, plus the slope in the y direction times dy. Those are separately the height that I gain in the x and the y directions. Or I could write that as partial z partial x times dx plus partial z partial y times dy. This generalizes easily to multiple dimensions. If I have a function that is a function of 3 variables or 4 variables, then if I want to consider how a little bit of change happens, then I can just add in the partial derivatives terms as needed. I want to talk now what seems separately as about a different topic, but it's going to relate in just a minute, which is the idea of the chain rule. So if I want to calculate derivatives of functions, say the functions that I have here, these are all simple functions, and I can calculate the derivative df dx using known rules that we know of. But what about functions that are a little bit more complicated? For instance, sine of 5x minus 8. Or 2x cubed plus cosine of x all to the 20th power, and so on. So these are a little bit more complicated to find the derivatives of, and in order to calculate the derivatives, we need to use the chain rule. And there's a really nice way to remember how to do the chain rule to calculate these types of derivatives. And so the way we're going to formulate the chain rule for us is we'll first define a new variable, u, which is a function of x, such that my function f is now a function of u, and it's a simple function that I know how to take the derivative of. Then, to find df dx, I can just take df du, that simple derivative I know, and then take du dx, since u now only depends on x. You might notice here that if you just treat these differentials as fractions, you could cancel the du's, and you're left with df dx. And that's one way to set up the chain rule to know that you're doing the chain rule right, is that you should always be able to cancel, put it in quotation marks, the differentials to get the derivative that you're interested in back. Let's look at an example. So let's look at this first example. F of x is sine of 5x minus 8. And we want to calculate the derivative of f with respect to x using the chain rule. So the first thing we'll do is we'll define u, which is everything inside of the sign here, as 5x minus 8, so that my function f, when written in terms of u, is just sine of u. Well, now the chain rule tells me that to find derivative of f with respect to x, I take the derivative of f with respect to u, and then I take the derivative of u with respect to x. So the derivative of f with respect to u is cosine of u. The derivative of u with respect to x is just 5. So this would be my derivative of f with respect to x, except I need to do a little bit more work because that u in cosine of u actually still secretly depends on x. And so I should substitute that in. So in particular, I should put that 5x minus 8 there, so that df dx in this case is 5 times cosine of 5x minus 8. So that's how I would use the chain rule to find this derivative. Now let's combine all of this together to think about the chain rule involving partial derivatives. So let me consider, again, some surface, z, which is a function of x and y. And now let me just give it explicitly so that we have something very explicit to work with, minus 2x plus y squared, for instance. Let me also then consider an object traveling on this surface with some time-dependent coordinates. So x and y depend on time. So x depends on time as v times t, for instance, and y depends on t as 1/2 a t squared. In principle, these could be any functions. I'm just writing something explicit down for us to work with. And what we want to know is how do we calculate the rate of change of the height of the object, dz dt. We want to know how fast it's moving in the vertical direction by only knowing the speed in the x and y directions and then what the height is for the x and y directions, that height function. Well, we can see that secretly z is a function of time because z is a function of x and y are both functions of time. Now, in principle, I could just plug those functions of time directly into z to get some horrible-looking expression in terms of time, but I actually want to use the idea of partial derivatives to think about this. In particular, let me think about this in terms of some kind of dependency diagram. So the height z, which is a function of x and y, depends on x and y each depend on time t. And so I can think about finding dz dt by using the chain rule. So I could think about dz dt as, well, in the x direction, I could take partial z partial x, the derivative of z with respect to x, times dx dt. Notice again that if you kind of squint and cancel the differentials, of course it's a terrible idea here because one of them is a partial and one of them is not, but if you squint at that, it gives you something that looks like dz dt, which tells you that you've at least set it up right. But since the height z depends not only on x, but it also depends on y, I have to add in that other term to do with the partial derivative with respect to y. So I have to add another term, dz dy times dy dt. So again, that looks like the chain rule, but it also looks like that combination of partial derivatives that we talked about earlier. Well, okay, so this is how we would formally calculate it. Let's do the example here. So we know what z is as a function of x and y, and we know what x and y are as functions of t. So let's do these derivatives. So partial z partial x should give me minus 2. dx dt should give me just a v. So that's the first term. On the second term, partial z partial y will give me 2y. And partial y, or derivative of y with respect to t, will give me a times t. I could try and stop there, but again, secretly, y is a function of t here. And so if I want to know dz dt as a function of, say, time, then I should plug in what y is as a function of time. And when I do that, I should end up with a result of minus 2v plus a squared t cubed. Now, you can plug this in, or you can check this rather, by taking the original surface, z as a function of x and y, plugging in for x of t and y of t to begin with, and then taking the derivative, so as if you knew nothing about partial derivatives and the chain rule, and you should get the same result. But this way of thinking about taking derivatives will be very useful in many circumstances. And so it's useful to think in this way in terms of these different dependency diagrams.